Hey there, folks. It is it's the 13th. I should have recorded this a couple days ago. I apologize. But this is chapter 20. We're going to be looking at weather today, and I apologize for the camera being so dark, but uh, we'll jump into the book here real quick so you won't have to look at my dark picture. But we're looking at chapter 20 today. We're going to look at weather. Now, this is a pretty important chapter simply because we experience weather every day, don't we? No matter where you live, you're going to experience some kind of weather. So it's important to understand these concepts and how weather works and what forces are involved so that you can understand a weather forecast and you can understand the processes that happen in weather. So let's jump right into the chapter here and talk about weather. So weather happens in our atmosphere. Atmosphere is made up of gas and gas is by definition a fluid, so it's affected the same way that water and other things are. So we've already talked about oceans and other kinds of fluids. So atmosphere as a gas works in very similar ways. In other words, the driving forces are going to be pressure and temperature, and they are interchangeable, and that's what drives our weather. So your book starts out talking about weather, and we think when we think of weather, we think of storms, uh, and storms are simply extremes of weather. Could be rain, ice, or snow. Excuse me. Um, so anytime we have extremes of weather, they usually involve storms. Um, so let's jump into where our atmosphere came from. So we know that the atmosphere formed about the same time the Earth formed, but it was a very different atmosphere. There were very different gases in the atmosphere. For one thing, there was no oxygen. Oxygen is going to come much later, and oxygen is going to be formed by photosynthesis. So there's a lot of carbon dioxide in the atmosphere. Because there was a lot of volcanic activity, we had lots of volcanic gases like sulfuric acid, methane, ammonia, those sorts of things. And so if you did go back in time and were back in a time in the early atmosphere, you couldn't survive. There was no oxygen. So oxygen is going to come, again, quite a bit later when we begin to see organisms that do photosynthesis. Most of this, what we call the third atmosphere here, most of this happens about 2.5 billion years ago, is when oxygen begins to saturate the ocean and rocks, the Earth's crust. In other words, oxygen's been produced for a while, but it's being absorbed in oceans and that sort of thing. But now it's gotten to a saturation point, so now that oxygen is available to go up into the air, and so this is what's beginning to change the atmosphere. Uh, it's going to take place over a very short, very long period of time, rather, and it's going to fluctuate over time. So today, we have about 20% of the atmosphere is oxygen. Um, your book talks about air pressure, and again, at the very beginning, I said that really the driving force of weather is pressure and temperature. So let's think about pressure for a minute. Air pressure, is simply the force of air caused by gravity. In other words, we think of air as being light, right? We think of air as not being uh, affected by gravity, but in fact it is. I mean, air molecules are matter, and so all matter is affected by gravity. So our atmosphere is around our planet because of gravity. If gravity went away tomorrow, which of course it won't, we would lose our atmosphere instantly. It would just float out into space. Um, so gravity is holding it down, and as you can imagine, closer, excuse me, the closer you are to your surface, the more gravity there is, and so the more pressure there is. So as you then leave, as you go up higher, higher, higher in the air, the air gets thinner. We say the air gets thinner. There's fewer air molecules bumping into each other. Therefore, the pressure is lower. And so that is, uh, even though there is higher pressure here, that pressure can change and fluctuate depending on the weather. And we'll talk about that in a little bit more detail. Um, Interesting little blurb here about air pollution. And again, this book was written a few years back, and a lot of this has gotten better. But we still have issues with a lot of the things they're talking about here. So go ahead and look at that. Um, so here we see a comparison of heat and temperature in the atmosphere. Now, this is something we have to discuss. So heat and temperature are two different things. We often think of something as having a high temperature as having a lot of heat. Well, that's sort of true. But you've also got to have a lot of molecules. In other words, um, as you go higher and higher in the atmosphere, you have fewer and fewer molecules, and at some point at that place, you're getting more and more heat. So each molecule has a lot of heat associated with it, thermal energy. But if you were in the atmosphere, you would still freeze to death because there's so few molecules. The only way you can get warmed up, if you think about it, down here on near the surface, we get warmed up because we turn on the heat, right, in your house. You turn on the heat, and what the heat is doing is it's heating up air molecules, and then those air molecules are bumping into you and giving you their heat. And so if you're out in a place where the air molecules have a lot of energy, have a lot of heat, but there's so few of them that you don't bump into them, then you're still going to freeze to death. It's kind of weird, I understand. But this is the difference between heat and temperature in the air. Great little blurb here. You definitely need to read this because this makes such a great test question. And it's one of those questions where people always ask, why is the sky blue? They don't really know, but if you read this and understand it, then you will know. So this is a really good one to understand, and also understand the sky's not always blue, is it? Sometimes it's red and orange, and depending on the molecules in the atmosphere, it could be a different color entirely. Like on Mars, we know that the atmosphere is red. So they don't have a blue sky, they have a red sky all the time in Mars. So let's talk just a minute here about one of the driving forces, or the driving force really, of weather, and that is the relationship between pressure and temperature. So there are certain laws of thermodynamics which say that um, temperature, as you increase temperature, um, you can and you do increase pressure in a closed environment. In other words, uh, if you had a container and you had air in that container, and you begin to heat the container up, heating the air up inside the container, the pressure would go up. Well, that makes sense because as you're adding energy, those molecules are moving faster. They're banging into each other harder and against the sides of the container harder. And that's what causes this higher pressure. Relatively true, too, is as you lower temperature, right, you lower pressure. So the pressure goes down. However, we can change temperature with pressure in another way. In other words, we can lower pressure and change temperature. Before we were saying we could take temperature and change pressure. We can also change temperature using pressure. In other words, if I have something which is under high pressure, some air that's under high pressure, and then suddenly I release the pressure, I lower the pressure, then what's going to happen is I'm going to lower the temperature. And again, sounds kind of amazing, but really it's what it makes your air conditioner work. It's what we use to refrigerate your food. And so this concept called adiabatic cooling um, is simply cooling caused by changing pressure. Reverse can be true as well. If I increase pressure, I can increase temperature. So the two are interrelated. I can affect temperature to I can change temperature to affect pressure. I can change pressure to affect temperature. Uh, now, we'll see in a minute what this got to do with weather. But let's talk just for a minute about the air and water. So we've talked about pressure, we've talked about temperature. Let's talk about water. So we know that in the air there is water. You're breathing in water right now. You can tell because if you had a cold window and you breathe against the cold window, you'll see water vapor cooling on the cold window. So, and that's what when you see your breath in the wintertime, you see your breath, you see smoke, what you're seeing is water vapor that is uh, that is condensing. Excuse me. Um, so we call this relative humidity. In other words, how much water is in the air is relative to lots of things, temperature and pressure, obviously. But if the relative humidity of the air, let's say, is 50%, then what that means is that half the air is holding as much water as it can. Once the relative humidity gets up to 100%, what that's basically saying is that the air can hold no more water. Uh, and we've all probably experienced this, like on a real hot, muggy summer day when the relative humidity is 100% and you're sweating like crazy and can't get cooled off. Because normally what would happen is as you're sweating, that sweat would evaporate, and that's what keeps you cool. But on a day where it's 100% relative humidity, now you're sweating. That water has no place to go but just drip off of you, and it's not very efficient for cooling. So that's what we mean by when you hear the weather person talking about relative humidity. That's what they're talking about. It's going to be important because high humidity oftentimes means rain. If you have very low humidity, relative humidity, then it's probably going to be pretty dry. Your book talks about clouds and cloud formation, very important, and latent heat of condensation. It's basically what causes a cloud to, um, or for water to release heat um, as it is as raining, basically. So here is a cloud, and your book goes into detail here. Excuse me, about the layers of the atmosphere. We talked a little bit about these in one of the earlier chapters. So notice that the atmosphere again is broken up into layers, and again these aren't hard lines. They're kind of gray lines. But the interesting thing here is to look at temperature. So if you're on the ground and you begin to go up, the temperature is going down, isn't it? And if you're flying in an airplane uh, up here in the stratosphere, the temperature is very, very low. So it might be 70 degrees on the ground, but if you're flying up here in the atmosphere, it could be minus 20. It could be 30 degrees below zero outside the airplane. But notice that it begins to warm up again, um, but then will cool off again and then get very, very hot in the ionosphere. Your book talks about this in terms of, and again, remember, up here there's very few molecules. So even though we have high heat, right, there's a lot of heat energy, you would still freeze to death in this area because there's so few molecules that could actually run into you that even though they have a lot of heat, they would definitely you definitely freeze to death. So go over this and look at the different parts of the atmosphere. Again, um, this is good stuff to understand, and you've probably seen this before in a high school science class or even a middle school science class. Because I know we've gone over it probably um, in those classes, but this is just kind of a review for you. Um, they talk about the aurora here. The aurora happens up in the ionosphere. and it's caused by the Earth's magnetic field. We talked a little bit about that in the earlier chapters. Um, so let's talk about another aspect of weather, and that is wind. So, what causes wind? What is wind? We can't see wind. We see the effects of wind, don't we? We can see leaves blowing. We can see trees moving. But we can't see the wind because it's part of the air. The molecules still are too far apart. The wind is basically caused by a pressure gradient. In other words, high pressure in one area, low pressure in another. You're going to have molecules moving from high pressure to low pressure, and that movement of molecules is wind. Um, One of the ways I describe it is if you can imagine a classroom, right? Two classrooms actually separated by a door in between. And in one of the classrooms, we've got 200 people. And in another classroom, you've only got about 10 people. And both classrooms are about the same size. You can imagine what would happen as you open the door, classroom with 200 people, people would start moving into the classroom where there's fewer people. And that's what happens with wind. In one classroom, we have high pressure, excuse me, the other classroom, low pressure, and the wind will move between the two. And that's really all that's going on. And this can happen again through pressure, but also since temperature can change pressure, we can see this in terms of temperature as well. Now, if you ever watch a weather report or see weather information, you'll see this pressure in terms of what we call isobars. And so you can see how the pressure is changing. A lot of times where it's warmer, you'll have higher pressure, and then where it's cooler, you'll have lower pressure. And as these two air masses, we'll talk about air masses in a little bit, as these two air masses mix and move, that's where we begin to see what we call high pressure systems and low pressure systems. And you'll see those again on the weather on TV or on a weather report. You'll see them as L's and H's with circles. And I think your book is going to talk a little bit more about those a little bit later. But one of the reasons we have these differences in temperature is again because the Earth is tilted. And so in the middle of the Earth, near the equator, right, is where we get warm weather. And because the Earth is tilted in relationship to the sun, the energy is spread out. Therefore, the energy that this particular area here receives from the sun is less. You can see if this is summertime in the northern hemisphere, you can see in the southern hemisphere, you may not get any sunlight at all. So that would definitely create a quite a temperature gradient, wouldn't it? Um, Here you can see these gradients a little bit better defined. There's kind of a general gradient again along this equator, and then you've got the temperate zone in the middle, and then here are the polar extremes. Here is that mixing that happens, and this is literally what we see on the weather, isn't it? Low pressure systems that rotate counterclockwise, high pressure systems that rotate clockwise, and all this mixing of air and changing of air is what causes our weather and changes that we see. Usually, high pressure is associated with nice weather. It literally is like the top of a hill. Everything rolls away from it. Water, uh, high pressure keeps everything away, keeps moisture away, keeps everything away. So if it's a nice sunny day and no clouds, it's probably thanks to a high pressure system. However, low pressure systems is just like a hole. Everything rolls into it. Water, um, pressure, temperature, everything. So a low pressure system will be a place usually where we have storms and rain. So if you see these lows, that's usually what causes. If you see a low coming, it's generally associated with some kind of a storm. Um, and so again, that's kind of a general thing, but for the most part, that's what we would see if we were looking at the weather report. Now you got some what we call prevailing winds, winds that sort of happen on a regular basis. Um, not winds like we think of um, um, on a weather report. However, if you stop and think about it, really, wind usually for us, for example, wind usually comes from the west and the south because that's where our weather comes from. So that's sort of a prevailing wind, but it doesn't always happen that way. Here you can see a map showing some of these winds and how this works. Um, your book talks about seasons and the tilt. We've already talked about the tilt of the Earth causing changes in temperature. But as the Earth tilts and goes around the sun, it can also create seasons. So we're entering the fall, or we're in the fall rather. We're getting ready for winter, which means we're tilted away from the sun. Therefore, that heat energy of the sun is being spread out over a larger area, and so we're not getting enough energy, and so the temperatures are going to go down. Um, a lot of times, if you ask someone this question, especially someone who doesn't understand this, and ask them why is it hot in summer and cold in the winter, they say, "Well, the Earth is closer to the sun in the summer and farther away in the winter." That's true in the southern hemisphere, but in the northern hemisphere, we're actually closer to the sun in the winter and farther away in the summer. So it is the tilt of the Earth that causes seasons, not the fact that we're a little bit closer to the sun in one season or the other. Here, your book talks about the jet stream, and you'll hear this a lot in weather forecasts because the jet stream does a lot to influence our weather. It's one of the things that sort of mixes up all those highs and lows and causes the interactions that can cause uh, temperatures to go down for a long time, temperatures to be high for a long time, rain to be pushed away, all these things. So the um, jet stream is very important in terms of general weather patterns and how that works. Here you can see kind of an example of that and how it works. A lot of times when the jet stream dips like this in the wintertime, it gets very cold. And this would be very cold air coming down and pushes the warmer air away. And then a lot of times the jet stream will move up and we can have a hot spell in the summertime or just brutally hot temperatures. So the jet stream does a lot to affect what we experience. Um, talk about weather and causes. We've already talked a lot about the different types of causes. Again, temperature and pressure are the biggies, and so here you can see some of the extremes in terms of pressure. Um, your book talks about, excuse me, your book begins to talk about air masses, and so a mass of air is a mass of air that has similar temperature and pressure, and it can meet a different mass of air that has different temperature, different pressure, and that can create what we call a front. And you'll see these on the weather map. You can have cold fronts, you can have warm fronts, you can have stationary fronts, you can have all kinds of different things. So when a cold air mass runs into a warm air mass, as you can see, the cold air is usually on the ground. Those usually happen very quickly. In other words, sometimes like in the fall or spring, it may be warm outside, and then all of a sudden this cold air mass comes in, and the temperatures can change drastically in just a few hours. Um, when warm air fronts happen, though, they usually happen over a longer period of time. So generally, when the temperature drops, it drops very quickly. But when it warms up, it seems to take a lot more time to warm up. Warm ups don't seem to happen as quickly as a cold front moving in can happen. There's an example of these warm fronts and cold fronts. The cold is usually depicted as a triangle because it's more direct. The warm fronts are generally these rounded edges because they usually happen slower and less over a longer period of time. So your book talks about cloud formation and precipitation. So precipitation is when rain falls or snow falls or sleet or something like that. So basically, water is in clouds in the air, and as water condenses, once it gets to the point where it can't stay in the air anymore, it'll come down as some sort of precipitation. Um, Very interesting little section here. So make sure you read this. Um, it talks about how you literally need how raindrops grow and how they move. There's all kinds of really neat studies that have been done about raindrops. Another really fun thing I used to tell my kids to do, um, and you can do this too. We're getting ready to come into winter, and hopefully it'll snow sometime this winter. But you can look at snowflakes. What I suggest you do is take a cookie sheet, paint it black, flat black, and put it in your freezer. Just kind of leave it in there so that when you need it, it's really cold. So once it starts snowing, then pull that cookie sheet out, and it's really cold. Go outside where it's also really cold, and have some snowflakes fall on it. And because the cookie sheet's nice and cold, those snowflakes will stay there for a long time. You can take a magnifying glass and look at them. They're just absolutely fascinating. So it's a really fun thing to do if you've got some kids or that want to look at snowflakes. That's a great way to do it. Um, so anyway, back to our chapter here. So we're looking at different kinds of clouds and different kinds of cloud formations. Um, these are some storm clouds, as you can see. You've seen these in the summertime with this anvil cloud forming. That's going to be some rain right there, and probably a lot of it. Here's a satellite image of cloud formation and clouds moving. So as you can see, they do kind of move in these sections, and they move based on wind and um, are part of these fronts and weather patterns, right? Um, Storms, we talked a little bit about those clouds, those nimbo cumulus clouds we were talking about are these what we call these supercell clouds. You've heard the weather people talk about these. These pop up because the air above the ground, when it gets like in the summertime when it's really hot, um, this moisture can form up in the atmosphere. The heat from generated over the period of the day adds energy to these things, and they get bigger and bigger and bigger, and then they can just drop an enormous amount of water in a very short period of time. There's a lot of lightning involved, and unfortunately, a lot of tornadoes. And again, this is a very interesting little section here because it talks about lightning and what lightning is, and answers the age-old question: does lightning go from the ground to the cloud, or from the cloud to the ground? And I'll let you read the chapter and find out how it works. So anyway, tornadoes can happen in these supercells, and tornadoes are essentially uh, when you have this much mass of air and water, these clouds begin to rotate. And just because they're rotating, it's not a bad thing. But if they begin to rotate quickly and kind of narrow their rotation, they can form these tornadoes. And if you've ever been in a tornado or seen a tornado, they're not anything you want to mess around with. They can cause a great deal of damage. And here you can see some pictures of some of that damage. Um, we're getting much better at predicting tornadoes and even predicting tornadoes um, by using new technology like Doppler radar. Doppler radar, if you remember the idea of Doppler, it's the idea that as something is moving towards you, right, the molecules are compressed, and so the if it's a sound, the pitch goes up. If it's light, the wavelength will change. So what this radar does is it measures um, this Doppler effect. And what happens in a tornado, if it picks up a tornado, what it sees is one wind is moving in one direction and another bit of wind close to it is moving in a different direction. So you can imagine that's that spinning of a tornado. And so it can predict where the storm is turning and what that might mean. Here's some scale factors for tornadoes. We talk about EF1s and EF2s and that sort of thing. And so this gives you an idea of where that information comes from and what kind of damage is involved. Most tornadoes occur in what we call Tornado Alley. It's right in this area here. So we're close to Tornado Alley, and we've seen our share of tornadoes, but they get a lot more of them in Indiana than we do here. And there you can see this image, this Doppler image. So where we see the reds and the purples, that's where the air is moving very quickly. But here, as you can see, air is moving this direction in one picture, and it's moving in that direction in another picture. So we're getting this rotation. And so a weather person who's trained to look at these things would look at that, what they call a hook echo, and see that that's a good possibility for a tornado. So that's good that we can kind of warn people. Um, your book talks about let's see, hurricanes. So hurricanes essentially are similar to tornadoes in that they're rotating storm clouds. They actually originate here in Africa, which is very interesting. So here's the Sahara Desert, and in the Sahara Desert, you get this wind moving in this direction, picking up all this heat, right? So it's very, very hot. So this very, very hot wind, very dry, hot wind. Suddenly it goes over the Atlantic. Very hot, very dry wind. And because it's very hot, now it's starting to pick up water. Water is beginning to evaporate into it. And so now it's collecting water, collecting water, collecting water. So all that energy now is being basically compounded, basically being fueled by this water. And now it's getting bigger and bigger and bigger, so that by the time it gets over here to where we're at, these storms can get very, very big. And now the water, of course, is very warm, and so that warm water helps to fuel the energy in the storm. And so by the time they get about in this area here, they can change into tropical storms. And then if the temperature, or the excuse me, if the air moves faster in a tropical storm, you get a hurricane. And a hurricane is sort of like this great big tornado, um, except they're just much, much bigger, and the winds aren't quite as fast as a tornado, but they do, excuse me, they do quite a bit of damage, which is interesting. We're in hurricane season now, and we have seen more hurricanes this year than ever before. This is caused by global climate change. We'll talk about that in the last chapter, but a lot of people who've been denying that climate change is an issue, we're definitely seeing the effects. Now, hurricanes cause damage in lots of different ways. Obviously, the wind can cause damage. Waves, because most of these hurricanes come from the ocean. They all come from the ocean, actually, and then go inland. So the waves, if you're living near the ocean, the waves can cause a lot of damage. But the biggest killer, really, of people is what they call storm surge. So as these storms evolve, as you can see up here in this chart, what's happening is these storms have very low pressure. Look at the pressure in millibars. This should be up around 1,000, 1,200. And as these storms are happening, the pressure is dropping and dropping and dropping and dropping. So as the pressure is dropping, literally the storm is getting bigger and bigger. It's literally sucking air right out of the ocean. And so it's this literally sucking of air. Now, what's happening right on the ocean itself? It's literally lifting the ocean out of the uh, out of out of the ocean. It's lifting the water out of the ocean. So the actual sea level right underneath these storms can be 10, 15 feet higher than a typical sea level. So when the storm comes ashore, not only is it bringing rain, not only is it bringing wind, but it's literally bringing the ocean with it. And the ocean can then, storm surge down here can cause enormous amounts of flooding and damage from that standpoint. Interesting studies of some hurricanes. Katrina, of course, was a very bad hurricane. I remember Hurricane Andrew down in Florida, because they sent me down there to help rebuild some houses. And I just remember seeing the devastation. It was just, I just had never seen anything like it in my life. The damage is just unbelievable. It's just a huge, huge amount of of damage. But yeah, we all remember Katrina. It was a horrible, horrible situation for New Orleans. So now we talk about climate. So what is the difference between weather and climate? Well, when we talk about weather, we're talking about day to day changes. When we talk about climate, we're talking about year to year changes. So climate is weather over a very long period of time. So when people who deny climate change come in with snowballs and say, "See, look, it's not getting warmer. Here, look at this snowball," or it's really, really cold outside. There is no such thing as global warming. They're talking about weather. They're not talking about climate. So it's very important to understand the climate is very different. And as climate is changing, it's going to affect our weather. In other words, we have more hurricanes this year than ever before, and a lot of these hurricanes are bigger than before. It's not that we haven't had hurricanes before, and it's not that we've had a lot of them and big ones before, but now they're coming in larger numbers and with more energy. That is caused by global warming and climate change. So, different types of climates are here, and um, you've probably, if you've been to or from India or any of the Asian countries, you know what monsoons are. Very interesting little article there. I was in Thailand one time to doing some help and some folks in Thailand, and I remember them telling me that tomorrow was the beginning of the monsoon, and it literally started raining the next day and didn't stop. So it's pretty predictable. It's really amazing. So let's see. Is there any other really important stuff? Read this section on El Ninos. We haven't seen any of these in a little while, although they were pretty important a few years back because they can cause quite a bit of damage. But it's basically a large area off the near the equator in the west of extra hot water that changes the weather pattern and can cause other places to really dry out because it sucks all the water out of the atmosphere and cause other places to get a lot of water. So anyway, do read this chapter carefully. It is really important and it's really really interesting. Again, we experience weather every day, so understanding how it works would be a really good thing. Here are your review questions on page. Yeah, I'm not sure what page that is, but you got plenty of them to choose from. And I will see you next time.